Today we're diving into one of the most fascinating and often misunderstood stories of human history, the origins of scientific thought. Recently, I came across a video suggesting that the Arab world essentially invented the scientific method and much of what we know as modern science. While that's a compelling narrative, it leaves out some crucial context. Humans invented science, but who exactly invented science? Can you point to a specific person? Are ideas born in isolation, or do they evolve as cultures exchange knowledge? Well, spoiler alert, it's the latter. History is full of examples of interconnectedness, of civilizations learning from one another, and one of the richest wells of this knowledge was ancient India. You've probably heard of algebra. Maybe not your favorite subject in school, but did you know its roots lie in ancient India? Also, the word trigonometry, known as trikunamiti in Sanskrit. Both trikuna and miti are Sanskrit words. Let's play a game. Can we calculate the size of the Earth with nothing more than a stick and a shadow? Sounds impossible, right? But let's prove it right now. Imagine this. It's noon and you're standing in two different places. In one spot, a stick casts no shadow at all. The sun is directly overhead. But in another spot, a stick does cast a shadow. Why is that? Well, we know that it's because the Earth isn't flat, it's curved. So by measuring the length of one shadow and knowing the height of the stick, we can figure out the angle of the sun's rays at the second location. Here's how it works. We'll use the length of the stick and the length of the shadow to calculate the angle of the sun's rays at each location using trigonometry. So angle x is the sun's angle for the stick with the shadow. Let's say in this example it's approximately 83 degrees. This can vary depending on the height of the stick and the length of the shadow. Now angle y is the location with no shadow. The sun is directly overhead, so its angle will always be 90 degrees. Now we have to find the difference in angles between the two locations. Suppose the angle difference in this case is 7 degrees. This difference represents the angle subtended by the Earth's curvature between 2 points. And now we'll use proportions to find the radius of the Earth. The Earth can be treated as a sphere, and the relationship between the angle and the radius can be expressed as this. And rearranging this equation gives the following. Finally, we also have to measure the distance between the two locations along the Earth's surface. Suppose in this case the distance between the two locations is 800 kilometers. Now, plugging all our known values into the formula, we find that the Earth's radius is about 6,371 kilometers. This value is close to the commonly accepted average radius of the Earth. And finally, to find the circumference of the Earth, we use the simple formula 2 pi r, and we estimate the Earth's size to be 40,000 kilometers. And that's startlingly close to the actual number. This method that we use to calculate the Earth's circumference is traditionally credited to Eratosthenes, who used rudimentary geometry and the differences in shadow lengths between two locations to estimate the Earth's size. But that's the twist. This method wasn't just about clever geometry, it also relied on trigonometric functions like sine and tan to calculate those angles. And who gave us some of the earliest, most accurate sine tables? Well, it wasn't the Greeks. A mathematician from ancient India, Aryabhata. Aryabhata, living centuries later, elevated this technique by introducing trigonometry through his sine tables. This way, he calculated the Earth's circumference to be 4,967 yojanas, where 1 yojana is equal to 5 miles, making the circumference 24,835 miles, or 40,000 kilometers. Aryabhata's contributions transformed what was a clever geometric observation into a sophisticated mathematical method. These sine tables allowed for precise calculations of angles and distances, providing more accurate measurements of celestial and terrestrial phenomena. Born in the 5th century in Kusumapura, modern-day Patna, Aryabhata was a mathematical and astronomical pioneer. The ancient city buzzed with intellectual energy, hosting scholars from across the subcontinent. Aryabhata's nights were spent gazing at the stars, his mind brimming with questions. Why do the stars move? What makes the moon change its shape? Could there be a rhythm to the cosmos? By the time he was in his 20s, Aryabhata had embarked on a quest to decode the celestial patterns, culminating in the composition of his magnus opus, the Ardh-Jya. The following statements are from the Ardh-Jya, and they comment on axial rotation of Earth. While many thought that the stars moved around us, Aryabhata correctly argued that it was the Earth spinning on its axis, a mind-blowing insight 1,000 years before Galileo. At first glance, Aryabhata's estimate the Earth rotates 1,582,237,500 times in a yuga may appear as a figment of metaphysical imagination. But it is equivalent to the surprisingly accurate statement the period of rotation of Earth is 23 hours, 56 minutes, and 4.1 seconds. In his work, Aryabhata also calculated the length of the solar year with astonishing accuracy, 365.358 days. One of Aryabhata's most revolutionary contributions to trigonometry was his systemic definition of the sine function. In the Aryabhata, he referred to the sine function as Ardh-Jya, which directly translates to half chord. Let's see the genius behind his ways. We know that a chord is a straight line segment whose endpoints both lie on the circle. The chord of an angle is the length of the chords between 2 points on a unit circle separated by that angle. Now the length of the chord can simply be calculated by using the distance formula, which is the distance between 2 points. For simplicity, here is the graphical representation. 2 sine theta is equal to 1 chord. So rearranging will give us sine theta is equal to half a chord. However, of course, an elegant formal proof is given in the Aryabhata. But now an obvious question might be, how did Aryabhata's Ardh-Jya become the sine function name that we use today? When Arabic writers translated Aryabhata's works from Sanskrit into Arabic, they referred it as jiba. Later, writers substituted this jiba with jiyab, meaning cove or bay in Arabic. And later in the 12th century, when these Arabic writings were translated into Latin, the jiyab was replaced with the Latin counterpart sinus, which also means cove or bay. And after that, the sinus became sine in English. Aryabhata's work in mathematics, particularly his introduction of sine tables and methods for solving quadratic equations, had practical applications for navigation, trade, and agriculture. A king might have used Aryabhata's astronomical calculations to guide ships through the monsoon winds of the Indian Ocean. One of Aryabhata's most remarkable achievements was his ability to predict solar and lunar eclipses. By combining trigonometric functions with his understanding of the Earth's rotation and the geometry of the Sun, Moon, and Earth, he calculated the timings and durations of these celestial events with impressive accuracy. Now, here's a challenge for you. I'm giving you a four-sided shape. It's weird, it has no right angles, its sides are all different lengths, and you're not allowed to measure anything inside it. Can you figure out its area? Well, what if I told you that 1,400 years ago, an Indian mathematician named Brahmagupta came up with a formula that makes this not just possible but elegant? Let me show you how. First, let's define what we're working with. This shape is called a cyclic quadrilateral. What makes it special? All four corners of the shape touch the edge of a circle. This unique property lets us unlock a beautiful solution. Imagine you're given the length of the four sides of this quadrilateral. Let's call them A, B, C, and D. The question is, how do you calculate its area without breaking it into triangles, measuring angles, or doing anything else complicated? This is Brahmaguptas Formula. The magic here is S, the semi-perimeter of the quadrilateral. We calculate it by adding up all four sides and dividing by 2. Let's take an example. Say the sides of our quadrilateral are 5, 6, 7, and 8 units. First, we calculate the semi-perimeter, which is 13. Next, we plug these values into the formula, and the area is 41 units squared. And there you have it. We've calculated the area of a complex, irregular shape, all thanks to Brahmagupta's genius. Brahmagupta lived in 17th century India in a time when geometry wasn't just about shapes on paper, it was about solving real-world problems. From designing temples to mapping the heavens, his work had a practical application in architecture, surveying, and even astronomy. Brahmagupta was a thinker of contradictions, on one hand deeply spiritual and on the other fiercely logical. He believed that mathematics was a divine language capable of revealing the secrets of the universe. In the year 628 AD, Brahmagupta wrote a treatise called Brahma Sutta Siddhanta, translated as The Opening of the Universe. Brahmagupta actually realized that mathematics needed a new number. In the treatise, he introduced one of the fundamental discoveries in mathematics. You guessed it, the concept of the number 0. Brahmagupta called the new number Shunya, which in Sanskrit means void or empty. Earlier Indian Hindu mathematicians had used placeholders, as in this example. This image shows a part of the Bakshali manuscript. The Bakshali manuscript is a 2,000-year-old ancient mathematical document discovered in a field by a farmer in British India. Decoded by researchers at Oxford University, it displays Sanskrit numerals in which, in the place of 0, is placed a small dot. The content of the manuscript covers square root computations to extraordinary accuracy, fractions, quadratic equations, and simultaneous linear equations. The creation of 0 as a number evolved from the placeholder dot symbol found in this Bakshali manuscript. Years later, Brahmagupta was the first person to define operations involving 0 systematically. He answered questions like, what happens when you add 0 to a number? What if you multiply it? Could 0 itself hold mathematical meaning? He declared that 0 was not merely the absence of a value, but instead a powerful tool in calculation. This work laid the foundation for modern arithmetic, algebra, and eventually computer science. According to Marcus du Sautoy, professor of mathematics at University of Oxford and lead researcher, this was one of the greatest breakthroughs in the history of mathematics. It was as early as the 3rd century that mathematicians in India planted the seed of the idea that would later become so fundamental to the modern world. Brahmagupta's brilliance was matched only by his stubbornness. He often clashed with rival scholars, particularly those who challenged his methods. Legend has it that he once spent an entire month proving his critics wrong, devising intricate proofs that not only defended his ideas, but also advanced the field of mathematics. What inspired him? Brahmagupta believed that understanding the universe was an act of devotion. He saw his mathematical work as a way to connect with the divine. Alright, now this challenge is for the hardcore math enthusiasts. Can you solve this equation? Sounds simple, right? All you need are integers for x and y. But there's a catch. It's not just any integers. The numbers have to fit perfectly, satisfying the equation exactly. And trust me, brute force won't get you far. Even for a supercomputer, this problem isn't straightforward. It stumped European mathematicians until the 17th century, when Pierre de Fermat set it out as a challenge. The equation we're looking at is a type of Pell's equation. It describes a hyperbola, a fascinating curve with two sweeping, symmetrical arms that stretch towards infinity. The equation of a hyperbola is pretty simple. Here, n is a positive number. The challenge is finding integer solutions, whole numbers for x and y, that makes this equation true. Let's take Fermat's infamous example. If you try guessing numbers randomly, you'll quickly realize this isn't a game of luck. The smallest solution involves x being a 10-digit number. What about integer solutions of x, y, and k, where k is equal to 1? Do all k's even have integer solutions? This is what medieval India was interested in. Medieval India not only had already solved n equals 61, but they had also found a generalized algorithm for all of n. What would have been Fermat's astonishment if some missionary just back from India had told him that his problem had been successfully tackled there by native mathematicians almost 6 centuries earlier. This is Bhaskara's lemma, generalized in the verses of the Bija Ganita by Bhaskara II around 1150. Let's decode it. Assume we have a triple ABK that satisfies x squared minus ny squared equals k. We can make another trivial triple by setting y equals 1. If x equals c, then this triple is c, 1, c squared minus n, and using the composition law, we get a new triple. For this triple, Bhaskara did something clever. He figured out that you can choose a c that makes each of the quantities in the triple divisible by k squared, thus making the new triple smaller than the one that came before. Then you can repeat the process until k is equal to 1. And since both equations on the left are squared, we can divide the entire thing by k squared. This gives us the following equation. Bhaskara described this entire process in 8 lines of Sanskrit in poetic verse. Bhaskara named this method Chakravala. Chakravala means wheel in Sanskrit, a perfect name because this algorithm works in a loop, refining the problem until it's solved. Here's a copy of the Chakravala code from GitHub. Let's try the code for n equals 61. He calculated that the smallest solution is a equals 1,766,319,049 and b equals 226,153,980. That's a huge number. And remember, this was solved centuries before Fermat's challenge even existed. European mathematicians centuries later marveled at this technique. It was not until the 19th century that Bhaskara's genius was fully recognized when James Taylor translated Lilavati into English, introducing Bhaskara to the global stage. Who are you? Well, Bhaskaracharya, the mathematician with a poet's heart. In the sunlit landscapes of Bijapur, Karnataka, in the 12th century, a young boy named Bhaskara grew up surrounded by the natural beauty of India's Deccan Plateau. His father, a learned scholar and astronomer, introduced Bhaskara to the mysteries of the stars and the rhythms of the cosmos. But Bhaskara's mind was equally captivated by the intricate puzzles of numbers, which seemed to dance with as much grace as the planets in the sky. As Bhaskara grew, his genius for numbers became apparent. But life wasn't just a series of equations, it was deeply personal. The story of Lilavati, his famous treatise on arithmetic, reflects this blend of intellect and emotion. Named after his daughter, Lilavati arose from heartbreak. According to legend, Bhaskara used his astronomical expertise to calculate the exact moment for Lilavati's marriage. But fate intervened. A pearl from her necklace fell into the water clock, disrupting the timing. The auspicious moment passed and the marriage was never realized. Heartbroken but resilient, Bhaskara turned his love for his daughter into a work of enduring beauty. Lilavati is a poetic exploration of arithmetic filled with problems that engage and delight. Through questions like, if a peacock stands on a pillar and a snake approaches its base, what is the distance between them when they meet? Or, if a swarm of bees divides into groups of 3, 5, or 7, how many bees are there? Yes, one of his most stunning achievements was solving Pell's equation, centuries before Europe even recognized it as a problem. But that's just one piece of his legacy. Bhaskara's work also included insights into calculus, astronomical instruments, and even the principles of gravity. The crown jewel of ancient science, Bhaskara's greatest contribution, however, was his magnus opus, Siddhanta Shiromani, the crown of treatises, divided into 4 parts: Lilavati, which covers arithmetic, Bijaganit, which covers algebra, Goladhyaya, which covers spheres, and Grahaganit, which is the mathematics of planets. This work represents the pinnacle of ancient Indian mathematics and astronomy. In Goladhyaya and Grahaganit, Bhaskara's understanding of planetary motion rivaled that of modern astronomers. He even articulated concepts akin to gravity, writing, "Objects fall on Earth due to the force of attraction by the Earth. This force allows the heavenly bodies to remain in orbit." Despite his genius, Bhaskara remained deeply connected to the world around him. His teaching style was said to be engaging and filled with metaphors, drawing analogies between numbers, nature, and everyday life. There is a widespread misconception that ancient India only introduced theoretical concepts, but lacked the mathematical equations to implement them. But you know what? As we have seen so far in this video, a lot of the mathematical formulas and equations were already encoded in the form of Sanskrit shlokas. Bhaskara's insights didn't remain confined to India. His works, along with those of the earlier Indian mathematicians like Aryabhata and Brahmagupta, traveled to the Islamic world, where they were translated into Arabic. This exchange laid the foundation for what later became known as the Golden Age of Islamic science. From Islamic scholars, these ideas made their way to Europe, shaping the Renaissance and beyond. The so-called Arabic numerals that form the backbone of modern mathematics, they are a gift from India, carried westwards by centuries of cultural and intellectual exchange. In fact, Al-Biruni, a Central Asian polymath who spent years in India during the 11th century, called Indian astronomy and mathematics ingenious, writing that their methods surpassed those of even the Greeks and the Babylonians. More of us should be questioning the double standard of how we name things when they're discovered by Europeans as opposed to non-Europeans, especially in math and science. Normally, we name things after the person who discovered them, to honor their work and their legacy. Like Euler's identity or Gauss's law. But when an Asian does it, Aryabhata's law, no, let's call it the law of science. The most frustrating one has to be the quadratic formula, because it's so important in mathematics and common as well. Every high school teacher has heard about the quadratic formula, and it involves two of the most brilliant minds in all of the history of mathematics, Brahmagupta and Al-Khwarizmi, and we call it the quadratic formula. Why? It gets worse though. Think about all the stolen credit. The Fibonacci sequence, not Fibonacci, known in India for hundreds of years. Even the Pythagorean theorem, not discovered by Pythagoras, known in Babylon, ancient Egypt, and of course, ancient India. This feels like a missed opportunity to teach people about how many different cultures contributed to our understanding of the world as we know it today. Science is a global, collaborative endeavor. The ideas that shape our understanding of the universe today, whether they're about algebra, optics, or even the speed of light, are the result of centuries of cultural exchange. Ancient India wasn't just a passive contributor to this process, it was a powerhouse of innovation and intellectual rigor. Let me know your thoughts in the comments, especially if there's something you think I missed.